An organic compound A containing only the elements carbon, hydrogen and oxygen was analysed. A was found to contain 54.5% carbon and 9.1% hydrogen by mass, the remainder being oxygen. Determine the empirical formula of the compound. So here our percentages we can just treat as mass and divide by the atomic mass, effectively the same as molar mass, and find the moles of carbon, hydrogen, oxygen, and from there we can get a ratio. So first things first, I like to use a table. So I'm going to put my elements here. So carbon, hydrogen, and oxygen. Now the mass, so I'm going to treat that percentage as a mass. So 54.5, 9.1. So that leaves, subtract from 100, 36.4% oxygen. Now mass, because I'm going to use the formula moles equals mass over molar mass. So I'm going to put the atomic masses in for these elements. 12.01 for carbon, 1.01 for hydrogen, 16 for oxygen. So to work out moles, I'm simply dividing the mass by molar mass here. So 54.5 over 12.01, 4.54 hydrogen, 9.01, and 36.4 over 16, 2.28. Okay, next, the last thing here that I need to do for my calculations is to find the ratio. To do that, all we need to do is divide by the smallest number there. So if I do that, of course, 2.28 divided by 2.28 is 1. So we don't need to calculate that. These two we do. 4.54 divided by 2.28. We get 1.99. So that's close enough. We can round that off to 2 because we're looking for whole numbers. 9.01 divided by 2.28. We get 3.95. So close enough to 4. So now we have our whole number ratios. So our empirical formula for this compound is C2H4O. Okay, now let's look at part B of the question. So that says a 0.23 gram sample of mystery compound A, when vaporized, we know it's become a gas, had a volume of 0.0785 decimeters cubed at 95 degrees Celsius and 102 kilopascals. Determine the relative molecular mass of the compound. All right, well, on this one, we're looking for two main formulae that we can use. So we know N equals mass on molar mass, which we can rearrange if we're trying to find the relative molecular mass. That's specific to molecules, but molar mass encompasses that as well. So molar mass is what we're looking for. So if we transpose that formula to solve for molar mass, we get mass over moles. Now the other thing we're looking for, we're dealing with pressures and volumes of finding moles of a gas. So we need PV equals nRT. In this case, we've got pressure, we've got volume, and we've got temperature. So we're solving for moles here. And of course, we've got the R value because that's a constant. Okay, so we're going to work back through this. We're going to take our volume there, and we're going to take our temperature, convert to Kelvin, temperature. We've got our pressure. We're going to solve for moles, and then we're going to use moles over here with our mass to solve for our molecular mass, which is the whole point of our question. Okay, so let's start with this equation here. Moles is equal to, now pressure and volume, the standard units of measurement for this equation, pressure we would give in pascals, and volume we would give in meters cubed. So we can convert those, but let's just have a look for a minute. If I put pressure here and volume, now if I was to convert pressure, kilopascals, that's 1,000 times bigger than a pascal. So I would have to multiply that by 1,000. Decimeters cubed, now they're 1,000 times smaller than meters cubed. So I'd have to divide that value by 1,000. So as you can see, these actually would cancel each other out. Multiplying by 1,000 divided by 1,000, we can actually get rid of them and simply not convert our units, provided we've got both decimeters cubed and kilopascals together in the same equation, because those changes will cancel each other out. So you can actually just leave those in the units that you've got. However, temperature you can never change, because temperature is an addition. To change it from Celsius to Kelvin, you must always, in any equation, you must always change it to Kelvin. So our R value, our constant value, we can see in our data booklet is given to us as 8.31. That's joules per mole per Kelvin, but I'm just leaving the units out. Here I'll run out of space. Multiply by the temperature, so 95 degrees Celsius.